But if you expect to get a spectrum like this, well, you're not going to get a spectrum like this. The spectrum is actually going to look a little more complicated. But that complication is what lends power to the NMR analysis. You will see what does. Now let's look at the protons over here. There are 3 protons, and what will happen to them the moment you apply a field? Immediately some of them will take this orientation, some of them will take this orientation. How many of them will take this orientation? About 20 ppm extra. We worked out that calculation. So if I had 2 million nuclei, maybe 1 million and something will take this orientation and 99,999 will take this orientation. The small x's will take this orientation, and then when you shine light or when you change the magnetic field or what happens? This guy goes this way, and you have a resonance, you have a peak. That's what we decided is the way the whole thing works. And then you always try to figure out at what field or what frequency this transition takes place, and a peak appears out there. But before we even go, why is this guy operating at a different frequency and this guy operating at a different frequency? The chlorine. It's drawing electron density away, making this guy less or more shielded. Less shielded, this guy continues to be more shielded, and that's the reason you get that. But that's not all. The story doesn't end there. What happens is, while this guy is trying to make the transition, what it really does is it looks at the neighbor. There are 2 protons out there. And what are those 2 protons doing? Are they up or down? Let me make it simple. CH2. Only 1 proton is there. Is that proton up or down? Well, in some cases it's up and in some cases it's down. In half the number of molecules it's up, and half the number of molecules this fellow is down. So when this fellow is trying to make a transition and looks there, some molecules are saying, yeah, this proton is up. In the other half of the molecules that actually is down. And mind you, there's a magnetic moment associated with this and this. So which means that this fellow's transition frequency, which is actually the effective magnetic field, and the effective magnetic field is what? The applied field minus the field due to the diamagnetic circulation because of the electrons. That's only one half of the story. What's the other half of the story? There's a nuclei sitting up there in which some of them are oriented up and some of them are oriented down. If they're oriented up, it actually reinforces the field for this fellow. But if it's oriented down, what happens? It's actually hurting the field for this guy, and therefore the field that this nuclei actually experiences is not just limited by the diamagnetic circulation, it is also going to be affected by the fact whether the neighboring nuclei is up or down. If it is up, this guy sees a little bit bigger, better field. If it is down, that's what is hurt. And therefore you will find that this fellow, some of the molecules, the metal phases a certain field. In some of the molecules, the metal actually phases a different field. And why is that? Because the neighboring nuclei is actually hurting it. And we call that a coupling. That's a very small effect, but it is very, very resolvable. You can actually see it in an experiment. So what do you think will happen to this peak due to metal? Will I get 1 peak or will I get 2 peaks? I should get 2 peaks. And different. It's a very small difference. What does this doublet really mean? The doublet really means that one of them has a Raman precession frequency corresponding to this, and the other one has a slightly different Raman precession frequency. And why is the Raman precession frequency slightly different for that fellow? Because in half the molecules, the adjacent metal, the adjacent hydrogen is oriented down, and in the other half is oriented up. If it is oriented up, this will feel a different field. Wherever it is oriented down, those nuclei feel a slightly different field. And therefore, the transition frequency or the resonance frequency is actually affected by the presence of the neighboring nuclei. And this is over and above the diamagnetic circulation of the electrons. The diamagnetic circulation of the electrons decides where this guy will absorb. The neighboring group proton, what does it do? It decides into how many peaks that fellow will split into. So if I have 1 proton, what are the 2 possibilities? One can be up, other can be down. And therefore, the peaks are just going to be a doublet out here. So if I see a metal occurring at somewhere near 1 ppm, and I see the metal is split into two, what does it immediately tell me? That metal has a neighbor with one proton. And you can see now, not only am I getting information about the metal, the fact it came at 1 ppm told me it is a metal. But the fact that the metal is split into two tells me that it has got a neighbor with one proton. And that's where the power of the whole technique really comes about. Let me make this way. Now what happens? The metal actually has to split again because there are two nuclei. If there are two nuclei, into how many will it split? How do I know it's 3? Why is it 3? Let's see, what are the possibilities? There are two protons. What are the various possibilities you can have? Both are up and up. In some molecules they are up and up. In some other molecules they are down and down. And what's the third possibility? One up, one down, or one down, one up. These two are same. But they are two distinct possibilities. They are same. We call them as degenerate possibilities. So how many distinct possibilities do we have? 3. How many ways can I get this fellow? 1. How many ways can I get this fellow? 2. How many ways do I get this fellow? 1. So which means, but what has happened in this case? If one fellow is up and one fellow is down, what has happened to their fields? So they have actually cancelled them out. Therefore they don't contribute anything to this guy. So this peak here, the metal is fellow here. All those molecules of the metal in which the adjacent protons are one up, one down, this doesn't contribute because these two guys are actually cancelled out. But all those molecules of where the two are up actually reinforces the field here. All those molecules in which both are down is hurting it. But all those molecules in which it is this way, nothing. So it would therefore come at the same place where no coupling ever took place. So what sort of a peak would I get over here? A triplet. I would get 3 peaks. But in what intensity ratios? Why this way? Because this is, let us say, due to this. This is, let's say, due to this. But this is due to this, and there are two such ways. Therefore, it's like if I ask you the question, if I toss 2 coins, what's the probability of head tail and tail tail? There's only one way you can get head. There's only one way you can get tail tail. But there are 2 ways in which you can get head tail or tail head. Therefore, the probability of getting a head tail is much more relative to getting head or a tail tail. It's exactly a 2-point toss problem. Therefore, you will see that the peak here for metal, this metal here, will not show up as a single peak. It will actually show up as 3 peaks. And what will be the relative intensity of the 3 peaks? It will be the ratio 1:2:1. And if you take the area of all these guys together, how many protons should that be? That should be 3 protons there. So earlier when I didn't bring the splitting into account, I just told you one big peak corresponding to 3 protons. What have I done now? I've taken the big peak, I've split them into 3, but the area under the 3 peaks together must still account for only 3 protons. And that's what you will get. So you have 3 peaks like this, and therefore you will get a triplet. But the moment I get a triplet, what do I know? A triplet at 1 ppm is telling me a lot. That it is 1 ppm tells me it is a metal. The fact it is a triplet tells me the adjacent carbon is actually having 2 hydrogens. In fact, if you have n equivalent protons, and what do I mean by that? These 2 are equivalent protons. If there are n equivalent protons, then the next guy will be split into n plus 1. Let's see what will happen to this fellow. Just like this guy got split by this guy must be split by this one. Yeah. Yeah.
So, the intensity would show at 1, right?
The intensity would show at a place.
Which means that the other hydrogen is not affecting CH3.
That's right. If these 2 guys are opposite spins, then the magnetic movement, because of this, it is not really doing anything over here, and therefore it would show up in a place at a point which it should have come if these guys made no effect on this. Right? That's where it should be, because this is actually a peak which is unaffected by the neighboring nuclei.
Can we say something about the distance?
Beautiful. Yes. That's called the coupling constant. And that tells me how much these two guys are talking to each other. And that's called a coupling constant. And mind you, when you learn more of this in great detail, you will actually be able to tell distances from coupling constant. Because the farther away they are, the less they talk to each other and so on. So that's what is, you can get the coupling constant by the distance, and that coupling constant actually tells me a lot about the way these nuclei are talking to each other. At this point in time, we are not going to push ourselves into getting that part of the information. At this point in time, we are simply going to use this splitting to tell me how many neighboring nuclei I have in a given situation. Now let's take this fellow and see how methylene is affected by the metal. If this guy can get split with this, there's no question that this guy will also get split by this fellow. I mean, it's mutual. How many ways can I get 3 nuclei to go? That's one way. And what's the other trivial way? And what's the other way? 2 up, 1 down. But then how many ways can I write that? 3 ways. I'm simply juxtaposing this down here, middle, and the other way. What's the other possibility? 1 up, 2 down. And then it's going to be, that's a possibility. And that's it. So how many possibilities do I have here? 1, 3, 3, 1. You see something emerging? Just 1, 2, 1. A square plus 2ab plus b square. And then a cube plus 3ab square plus 3a square b plus b cube. Another triangle. That's exactly what's going to happen here. So if you have n equal hydrogens, you will actually generate a Pascal's triangle, and that will tell you in how many ways the peaks are going to split. So if this fellow is going to split this fellow into a triplet, what will this fellow split this into? A quartet. It will be 4. And what will be the intensity of those 4, and what ratios will that be? So this will not be a singlet anymore. It will be 1, 3, 3, 1. So if I see a peak at 1 split into 3, I know it's a metal with an adjacent methylene. If I see a peak somewhere around 2, I know it's a methylene, but because it is split by 4 into 4, I know the neighbor must be a triplet. And immediately I know there's a metal and a methylene sitting next to each other. And that's how you start getting information on all of this. What happens if I take a molecule such as this? How many peaks will I get in NMR? For that molecule. How many peaks will I get in NMR? 2. Because this will give me 1. But these 2 are related by symmetry. Therefore, they must be equivalent. Or I'll get 2 peaks. Okay, then what will happen to this fellow? Into how many peaks will he split? I mean, this or this. It's got 2 neighbors, and therefore, this fellow should actually show up as a triplet, but then this and this are the same. Therefore, you will see a triplet. And why a triplet? Because this, or for that matter, this, has 2 hydrogens as its neighbors. And if I have 2 hydrogens as its neighbors, 2 equivalent hydrogens as neighbors, then how many peaks do I split to? 3. How many will this split into? There's a hydrogen here and a hydrogen here. I can therefore write all the possibilities. This flow up, this flow up. This flow up, this flow down. This flow up, this flow down. Or both down. So how many possibilities do I get? 1:2:1. And therefore, this flow will be split into Again a triplet. But why a triplet? Because there are two equivalent hydrogens actually flanking it. So when I give you this problem, don't forget that there are two guys sitting in there and both together will actually cause the splitting. So this fellow will be split into a triplet because there are two hydrogens. This fellow will be split into a triplet because it has two hydrogens, and then we will get two triplets, one corresponding to a CH2 and the other corresponding to a CH on which there is a Cl2 attached to it. So the point we're trying to drive home over here is that the place where the peaks actually occur on the delta scale tells me what sort of a group it is, and the number of peaks it splits into actually tells me how many neighbors this fellow has. And this is what we call as coupling or J coupling. Just use the word coupling, meaning that the spin of this proton, for example, is actually coupled to these, or the spin of this is coupled to this, and this coupling actually adds one more dimension to the whole process, in addition to the diamagnetic circulation. So first what happens? You apply a field, this fellow starts to precess. And just when you think this guy is going to precess at a certain frequency, in comes the diamagnetic circulation. And what does it do? It changes the frequency of this precession, depending on whether it is shielded or more or less shielded. For a bare proton, we know it's got a certain frequency. You bring in the diamagnetic circulation, the frequency changes because of the shielding. And now you bring in the coupling, it changes even a little bit more. It could be higher or lower depending on what sort of orientation you have on the adjacent nuclei. And this is actually extremely powerful. And in fact, what you do is you can draw a tree diagram to explain this. We just write the tree diagram.